Hey guys, well, I still have something that resembles a voice as I cough. Um, I'd like to kind of walk you through the example in more detail that I talked about today. So my voice is shot. Sort of hard to get done the amount of stuff I need to do, as you can tell. So I'll do the best I can here to sort of motivate what I was talking about with the Stokes trick and the examples that we use to do that. So I'm going to remind you that the basic idea of Stokes theorem is that we use it on domains that look like this. So Stokes theorem applies to surfaces with boundary. And the sort of prototypical picture of that is you've got some kind of sheet floating around in space and some kind of edge on it. And this is the boundary of the surface. And I know it's irritating that to use S for both the surface and the component of integration here. So maybe I'll call this, maybe we can assume it's parameterized. So let's just call this X of D. Some parameterized surface. We're going to assume it's smooth and oriented. And the way to set the orientation on the surface is I need to make sure that I have a sort of an up direction that I've chosen. And then I think about the way that curves move inside the surface as they go around the orientation vectors and sort of corresponding to a right-hand rule. You hold your thumb straight up to indicate the direction that the vector is pointing, and then the way that your fingers curl around tells you how the orientation should wrap around that vector. So that induces a orientation on the boundary. So if you have upward pointing orientation, then the boundary is going to orbit this way. The idea is that the orientation of the boundary is supposed to make it so that it's sort of to the left is the surface. So that's over here. Okay. And remember that I mentioned in class that the sort of real version of the 2D Stokes theorem is this relation. If everything is nice enough, so assume everything is nice, then the double integral over the surface of the curl is equal to the single integral path integral of little x around the boundary, where x is some path corresponding to the boundary. And since it's a path integral, that's f dot little ds. Okay. So keep in mind here, even though it's hard to see when I'm drawing these words, the d big S is equal to n of st ds dt corresponding to some parameterization, and little ds is equal to x prime of t dt corresponding to some different parameterization of the boundary curve. Okay, this is a line integral. This is a surface integral, which is why we have two different kinds of ds, as Connor pointed out in class. Okay. So let's actually walk through the example I did on the board, and I'll try to do it in more detail so it's clearer what's happening. If we let a surface, say x of d, and even s of d, let's just look at the surface given by z is equal to e to the minus x squared plus y squared over the disk x squared plus y squared is less than or equal to 1. And what that means is that the smallest value here of the surface is the height z is equal to 1 over e. And the surface kind of has this shape, sort of a Gaussian normal curve looking thing. And then it has kind of a sombrero shape, and on the edge is a curve, and the curve is just a circle. So this is the surface x of d, And this boundary curve is just the circle of radius 1 and height 1 over e. Okay. So somebody comes along and gives you a vector field. And that vector field is chosen to be particularly ugly. F is equal to e to the y plus z minus 2y I plus x e to the y plus z plus y j plus e to the x plus y k. And you're given the command, or you're working in a situation where it's actually important for you to calculate the curl of the vector field through the surface. So that is, you're tasked with this. What is the double integral over x of the curl of f through the surface? And this is hard. It's hard because the pieces are hard. So the curl of f is actually not so bad. We can compute that pretty quickly. So the curl of f here, the first thing you're like, oh, well, maybe I can do it. I'll start with the curl and see what the curl looks like. So you compute the curl and you get this. E to the x plus y minus x e to the y plus z, comma, oh, in the I direction, I guess we could use component notation. E to the y plus z minus e to the x plus y, j, and then only 2k. This is your hint. This is what I didn't get to in class today. This is your hint that the curl is particularly simple in the z direction. That's only a constant in the k direction, which means if we could somehow replace the surface with a better surface, then we would just be taking a dot product with the vector with a 2 in that component. So you continue on, right? We've got curl computed. Let's look at what ds looks like for this problem. Well, n for the original surface, if we compute the normal vector n, you end up with 2x e to the minus x squared plus y squared I plus 2y e to the minus x squared plus y squared j plus k. And now we have to dot these things together and integrate, which is gross. It's yuck. So the particular expression that we get from n here comes from the fact that we have this surface characterized as a function z of x and f of x and y. That's how you get this expression for the normal vector. Here's this is terrible. This is not something that we want to do. So what can we do? Well, I can use the Stokes trick, which says that, like, if I don't want to compute this big, horrible, ugly mess, I can replace it with a dot product with a normal vector that's a lot nicer. I mean, this normal vector changes everywhere on the surface because as you move around that sort of hat shape, your normal vector shifts as you do that. So the first attempt at the Stokes, the application of the Stokes theorem is to say, okay, maybe what we can do instead is we can look at the integral over this circle. The circle, remember, is the circle that is radius 1 and height 1 over e, sitting in R3. So we can parameterize it. I mean, it's pretty easy to parameterize. One parameterization for this is x of t is equal to cosine t sine t 1 over e. And where t goes from 0 to 2 pi. And that will parameterize the path. So what we've done is we've thrown away the surface, and now we're just looking at the boundary. Okay. So we reduce this surface integral into a line integral, and we think, I can do it now. Stokes theorem says I can do this. So I try to compute this. So it's going to be the integral around the boundary of x of d surface of f dot d little s, which is equal to, okay, so I've got that path. So to integrate from 0 to 2 pi, I'm just going to take the field and I have to plug in my path. That's what I do when I do this. So I'm going to get 2 sine squared t minus sine t e to the sine t plus 1 over e plus cosine squared t e to the sine t plus 1 over e plus the cosine of t sine of t dt. And you have no chance of integrating that. I think you're just not going to do it. Nope. So now I struck out twice. Tried the surface, and we got something that basically is not integrable because I can't deal with these things integrated together. I have no idea how to integrate these mixtures of all these x's and y's and z's. And then I use Stokes theorem to say, well, up here I was looking at the double integral over x of d of the curl of f dot d big S. Maybe I can reduce that to a single integral of f over the boundary dot d little s. And that was still bad. So what we're going to do is we're going to say, okay, well, maybe I can cheese this by picking another surface that has the same boundary. Because all Stokes theorem says is that the curl through a surface is equal to the circulation through the boundary. It doesn't actually tell you the shape of the surface. If you knew the circulation through the boundary, then you know the curl through any surface that has that boundary. So we're going to go, this is the integral I was originally interested in solving, was this. Curl of f dot ds. So I replaced that with an integral around this boundary, double integral over the boundary of x of d of f dot d little s. But that's equal to, so I guess I'll color maybe the surface pink here. And there's no surface in this. This is just a line integral around the boundary. And what Stokes theorem says is I can put any other surface inside that boundary I want. And a particularly convenient surface to pick in this case would be a disk, because if you notice that we compute the curl of f here, curl of f is really simple in the z direction. So what I'm going to do is I'm going to say, well, I'm going to solve a different problem that's equal, which is this problem. I'm going to do this disk. I'm going to calculate the curl in that disk. And Stokes theorem says that the curl through that disk is the same as the curl through this surface. So by Stokes theorem, these are equal. I'll call it x1 of e of the curl of f dot ds. It's a striking feature of Stokes theorem that this is true. It has to do with the way that the structure of vector fields. So why would I do that? Well, the normal vector to this disk is always just pointing straight up. So I'm going to use a slight reformulation of Stokes theorem to finish this computation. And the slight reformulation looks like this. So we're going to say that the double integral over the original surface x of d of the curl of f dot ds, which is equal to the double integral over the new surface x prime of d. These must be the same because they share the same boundary. And then we're going to do this trick. This is actually equal to double integral of x prime of d of the curl of f dotted with the normal vector and ds without the vector hat on it. Remember we did that trick before where so the move here was d capital S is equal to n ds dt, which is equal to n times the length of n ds dt, which is equal to a unit normal vector n times ds without the vector sign. So now I'm computing this, the curl of f dotted with a unit normal to the disk. Okay, so what is the unit normal to the disk? Well, the disk is flat and it's parallel to the xy axis. So the unit normal vector to the disk that we've plugged into this boundary, little n, is just 0, 0, 1. So if the curl of f was equal to whatever madness it turned out to be equal to, you can just grab it and bring it down, I guess. Last tool here. Grab this normal vector. Oh wait, that's not the normal we wanted, it was the curl. Grab some curl. And should be able to copy that. Can I copy it? Copy. Here. Let's see if I can paste it. No. Maybe I can do it like this. Nope. Well, trying some strong technical skills here. And I don't want to do it again. That's right. Touch it, copy it. There we go. I was after lazy. Okay, so that was curl. And the normal vector that we chose here, n, that we found for this particular surface, n was equal to 0, 0, 1. So that means the dot product of the curl of that normal vector is 2. Because 0 gets multiplied by this, and 0 gets multiplied by this, and 1 gets multiplied by 2, and you get 0 plus 2, which is 2. Well, that's nice, because it means all of this nonsense reduces to an integral that looks like this. The double integral over the surface, parameterization of the surface of 2 ds. And that's just equal to 2 times this integral, which is just the surface area, just area. The surface is a disk. So its area is pi, circle of radius 1. Right? This is a circle of radius 1. This is 2 pi. That's the sort of thing you can do with Stokes Theorem. Is you can, reduce these sort of complicated problems to simple ones in some cases. And the idea of taking a complicated surface and replacing it with a simple one is kind of a core technique in the application of these ideas. So I suppose I need to also sort of mention the divergence theorem, which is the last thing that I want to talk about. So the divergence theorem connects the 2D version of Green's theorem, the divergence 2D Green's theorem, to through the full 3D version. So Gauss's theorem which is also called the divergence theorem, says that basically the flux of a field through a closed surface is equal to the total internal divergence. So by closed surface, I mean like a ball or sphere or something where it like wraps back around on itself. And the idea is that when you have that, you can tell how much, when there's a relationship between the amount of the vector field that's pushing out of the surface and adding up all the little divergences on the inside. And so the statement of the theorem is, typical set of nice conditions. D now is a bounded solid region, which just means it has a closed boundary. In R3. So I think of the boundary and the interior now. With boundary of D being equal to apparently many smooth oriented surfaces. Oriented away from D. So what I can picture here is a ball. So the D part is the inside of the ball, and the S, the boundary, so D is the middle. D is the middle of the ball. And the boundary of D is the sphere on the outside. Remember, spheres are hollow. And we pick the orientation, so that the orientation points away from the region. So it's an outward-facing orientation. Then what the divergence theorem says, if you have a C1 vector field, if F is a C1 vector field, is exactly the same we said, which is this double closed integral through the boundary of F not ds is equal to the triple integral on the interior of del dot F. And this is saying flux through the boundary is equal to total divergence inside. And these three theorems together sort of are the, Green's theorem, Stokes theorem, and Gauss's theorem are the three central theorems of vector calculus. So I have another example of the sort of application of Stokes theorem. You should be able to assign a question that talks about working with Stokes theorem indirectly. The same kind of game can be played there. You got to keep in mind, I can't ask an incredibly complicated question with Stokes theorem because these integrals can be so hard to compute. So in this version that we did up here, this integral turned out to be particularly easy to evaluate once we use the trick. So if you see something like Stokes theorem on the final, it's going to be of that ilk, but without all of the sort of preliminary work. It would just be like apply Stokes theorem to create a new surface and integrate through. I'll give you examples. Okay. So for those of you that decide to watch this, thanks for taking the time to finish up the content with me. And I wish we had another couple weeks. We could keep going. This class already has a lot of stuff in it. And yeah, it'd be cool to take some more time. If you like the kind of math we did in here, you should consider taking 404, which is differential geometry, sort of the study of calculus on manifolds, which are surfaces in higher dimensions. All right, I will make another video if it seems necessary. So I'll see you guys soon. Take care.